I can check there, but
Welcome back, everybody. It's a pleasure to introduce Paul van Dooren, who most of you already know. He's from the University of Louvain. I remember in the 70s, I think Paul was another visitor to Stanford.
79.
79. And I remember Jim Wilkinson coming back because he'd been there as well. And he said, I've met this promising young numerical analyst who's working on the Kronecker form, which was something Jim was working on at the same time. And I think Jim was quite kind to Paul at the time, wasn't he? So very pleased to welcome Paul.
Thank you very much. And thank you to Nick and friends for inviting me for this meeting. It's a real honor. And I chose a topic that actually went over many years. First, I worked with Damien Lemonnier in the beginning on this problem, and then I read a thesis of Mr. Knight, which was a student of Nick Hyam, and that helped us go on with this problem later on. So it's about diagonal scaling of matrix pencils. So we're going to talk about eigenvalues, which I think everybody will appreciate. Okay. So I'm going to talk about generalized eigenvalues. So we are looking at the roots of the pencil lambda b minus a. A and b are both square. That's a polynomial of the degree n in general. And these eigenvalues is what we are interested in. And we would like to massage the matrix a little bit or scale rows and columns so that the sensitivity of the eigenvalues is improved. That's what is called the diagonal scaling problem of matrix pencils. It's very similar to the diagonal scaling that you're familiar with in the eigenvalue routine I, where you do balancing. There is a similarity transformation, but for pencils, it's an equivalence transformation. We will do transformations both left and right. Doesn't change the roots of the eigenvalue problem, of course. Yes.
You've got some people over there.
Oh, okay, I'm sorry. I should also stand there, right? And so the type of scalings we will do are diagonal scalings with powers of 2. That means that you can make them without any rounding errors, because it's just the exponents of each numbers aij and bij, which are scaled. And so there's no rounding errors in this process. And you do that before you apply, for instance, the QZ algorithm to find the eigenvalues. And you would hope that this diagonal scaling will improve the sensitivity of the eigenvalues and therefore improve the computation of the eigenvalues. And there were two methods in the beginning that were available. Well, the first method was Ward's method, actually. I think Bob Ward was a student of Cleve Moeller, I believe so. Anybody can confirm that? Okay, who was his advisor?
I think Ortega.
Oh, it was in Texas, I think, right? That he did a thesis anyway.
Well, he was at the University of Tennessee.
Yeah. And so the balancing idea that he had is to try to make all the elements in the two matrices of about the same size, which you cannot always do, of course, because you have two n parameters in DL and DR, which are diagonal matrices, and there are two n square parameters that you would like to balance. That's impossible. But anyway, this was a very good idea, and it improved the sensitivity of the eigenvalue computation quite often, but not always. And actually, it could also severely deteriorate the accuracy of the computation, as we will show in a few examples. And then this was in 81. And 25 years later, I had a student, Lemonnier, who worked on a modified problem. And there, the idea was to try to minimize the condition number, so the sensitivity of the eigenvalue problem. And we tried to find an expression for this condition number and then see if with the diagonal scaling we could improve that. And the condition number for the generalized eigenvalue problem, first of all, you have to be able to also talk about perturbations of infinity. So you have to introduce another metric. the generalized eigenvalue problem was not typically defined in terms of lambda b minus a, but using the homogeneous formulation, alpha b minus beta a, rather, and then the eigenvalues are just ratios of numbers. Okay, and there is a metric to measure how these ratios of numbers are being perturbed, and that's called the chordal metric. Alpha beta is a number in the complex plane. Gamma delta is another pair in the complex plane, and if you take a line between the origin and alpha beta, and a line between origin and gamma delta, then the angle between these two is the chordal metric between these two relative numbers. That's the expression. Okay, and it was shown in Stewart and Son that actually the QZ algorithm performs a backward stable decomposition. Therefore, the computed eigenvalues are exact eigenvalues of slightly perturbed matrices B plus F and A plus E, where F and E are much smaller than B and A, of course. And they show by error analysis that the chordal metric of the error that you perform with the QZ algorithm is bounded by this expression. Therefore, this quantity here is like the sensitivity of the eigenvalue, right? Because if I apply the QZ algorithm, this is what you lose essentially times epsilon. So it's the sensitivity number. So that's the quantity that we should try to minimize, in a sense, to improve the conditioning or to improve the sensitivity of the eigenvalue problem. Okay. I'm looking now. Okay, also on this side. Okay. And it turns out that this quantity, you can find which pencils have a very good sensitivity. Okay, this was shown also in this thesis, that if I minimize by the norm of A and B multiplied by these transformations TR and TL, which are invertible transformations with determinant T equals 1, if you minimize that, then you actually minimize this as well. Okay, so the idea would be then, first of all, what are the pencils that have an optimal sensitivity, that have a minimal sensitivity? It turns out that these are the so-called standardized normal pencils, which is an extension of the idea of normal matrices in the standard eigenvalue problem. Remember that the normal matrices are the ones that have an optimal condition number. It's 1 in the standard eigenvalue problem, because they can be diagonalized with orthogonal similarity. Okay, and here the normal pencils are the ones that also have left and right orthogonal matrices, and moreover also have a particular scaling on the eigenvalues themselves, which makes sure that this is actually minimized. In the Frobenius norms, it's bounded by square root of n, and in the 2 norm, it's bounded by actually square root of 2, which is almost optimal. So these are the interesting pencils, and this is the interesting scaling you should do. But this is for full matrices, n by n square matrices. And we are only allowed to do diagonal scalings with powers of 2. And then, of course, you cannot attain this, but you can try to get as close as possible to these pencils that will probably have a minimal condition number. And that's what we will do. And if you do that, so if you mimic the decomposition we just had with diagonal matrices, that hopefully will have an improved condition number. And in practice, it does. The question is, how do you minimize that? And it turns out that at the minimum of this is an optimization problem. If you write down the first order optimality conditions, you find that actually what you have to do is to make sure that the columns of A and column of B in 2 norm add up to the same quantity gamma square, and as well for the rows of A and B next to each other. In other words, if I put A and B below each other and next to each other, you have to make sure that the columns of AB and the rows of AB all are equal. And if that's the case, then you have found the optimization of this optimum. Okay. The constant gamma is not really important. it's going to be balanced for every gamma as long as it's constant for both columns and rows. Okay. And therefore, the LVD scaling will likely improve the error computed of the computed eigenvalues measured in that chordal metric. Okay. I should remind you that actually DL and DR will be only powers of 2, so there will not be an arbitrary, this will not be completely reached because the minimization is over a discrete, well, so-called discrete set. They have to be powers of 2, and therefore these equalities are never really reached, but they are approximately reached. Okay. And so here's the algorithm to do that. You take gamma equals 1 because gamma is not really important. You start with a diagonal scaling, and then you look at the matrices AB, and with an updating of the left and the right transformations, you make sure that all the columns have norm 1. Okay, and that's very easy to do. That's always possible. You compute these norms if they're, and then you divide so that they become norm 1. Okay, if the entries of the diagonal matrix are restricted to be integers, the process converges in general quite fast. And see, so we published this result in 2006, and we were so proud of this algorithm that we added a little MATLAB code in it, and then afterwards, we learned that this is a well-known algorithm actually, and I will come back to that. But it worked well. And I would like to give a number of examples to show that. And so what we will do is we'll compute the chordal metric of the exact eigenvalues that were planted in the pencil and the ones that we computed. So this is the forward error in some sense. For each eigenvalue, and we put that in a vector, and we look at the norm of this vector. So this is the norm of the computed sensitivities in a sense, okay? And here are some examples. So what I show you is the QZ algorithm directly applied to the original pencil without scaling. Then the QZ algorithm applied to the scaled pencil. And we will try to see if this improves. And then also the QZ algorithm applied to the word scaling. And here you see the 3 numbers. So the original matrices had that. This is one of these examples where the word method actually did worsen the sensitivity, but the balancing that we had here worked reasonably well, and the errors are all of the order of 10 minus 15, which is what you would expect, or what you would hope for in the best. Okay. Here's another example that comes actually from a paper of Françoise, I think. This is a second order polynomial matrix with Françoise and Meerberg, I think it came from, which you can turn into a pencil. And there we use 3 different methods. Since this is a polynomial matrix, you can use poly-arg of MATLAB, which is for polynomial matrices. Or you can solve directly on this pencil without scaling, or you can solve it with scaling. And you can see that there is a tremendous improvement, but it turns out that this is a problem which is easy to improve. I think you also used tropical, that really, so in this sense, this is a problem that actually is badly scaled from the very beginning. The data are given in poor condition. Anyway, so this is the method, seems to work well. But in fact, if you look at it, the scaling that we do with these diagonal matrices here can be shown to be equivalent to another algorithm. So if you satisfy these conditions, which were the conditions that I mentioned before, that the column and row norms are all equal to 1, you can interpret that differently. You form this matrix here, which is the Hadamard square of each element in A, plus the Hadamard square of all elements in B in absolute value. And you do that also for the scaled matrices A and B. It turns out that this transformation here can be written down as such a transformation. So in fact, what we were doing on this matrix is to do a two-sided scaling to make it doubly stochastic. And that's a very classical algorithm, which I didn't know about when we wrote that paper. This is the classical problem of take a matrix M, non-negative, and try to find two-sided scaling to make it doubly stochastic. That's exactly what these conditions are about. And that's a topic of the thesis of Philip Knight, which was a student of Nick Heim. And so thanks to that, we realized that what is the algorithm that's behind there and why does it converge? And so there's a very nice analysis in his thesis, or well, actually we read the paper of 2008, I think. It came later then. And so then we started to extend this and better understand this algorithm. So there are many results in the literature. Actually, it goes back to Kruithof, 1937, Sinkhorn-Knopp, that's the name I heard from the paper of Knight, and many other people have worked on this problem. Okay. And in the paper of Knight, we found necessary and sufficient conditions for this to work, because we mainly tried it on matrices that are dense. And then there's never a problem. These things always converge. But it turns out that the conditions for convergence of this algorithm are known, and they were in the work of Sinkhorn-Knopp, and I believe that's why it's now called the Sinkhorn-Knopp algorithm. They were the first one to really analyze this algorithm correctly. And they show that the following result: there exists a doubly stochastic matrix with diagonal scalings if and only if M has total support. I will explain in a minute what total support means. And if M still exists, then it's unique. And DL and DR are also unique, provided M is fully indecomposable. Okay, these are two conditions on zeros being on the number of zeros that you have in the matrix. And rather than explaining exactly what total support and fully indecomposable means, let me give you an example. Here's a little 2x2 matrix, which has 1 0, but that 0 is in an embarrassing spot. And if you try to do the diagonal scaling, you can see that the conditions that have to be satisfied are written there. And there is no bounded solution for this set of equations. There's either one of the S's has to be, one of the S's or T's has to be 0, and the other one has to be infinite. So there is no bounded solution for this. It's impossible to solve it. But if you think of it, if you run this Sinkhorn-Knopp algorithm on this matrix, it's going to diverge. Okay, the diagonal matrices will go either to infinity or to 0. But if you only do a few steps of this algorithm and you stop early and you use powers of 2, you get a perfectly acceptable scaled matrix. So you don't have to go full convergence. You just stop as soon as it's more or less norm 1. And that's what we did without thinking in this little code, is that we had a stopping criterion that as soon as it's a factor 2 of the result, you stop. And then it converges in reasonable amount of steps. In all the experiments that we did, we were probably rather lucky in the beginning. And it's later on that we tested this more aggressively on sparse matrices, and then you can have surprises indeed. But from this link to the thesis of Philip, actually we realized that we had to go a little bit further and dig into this problem a little bit more. How am I doing in time? All right. Okay. So, oops, I shouldn't have done that. Okay. Okay. Go back, forward. So what should we do when this algorithm does not converge? And so we started to think of that. And actually, when it does not converge, what typically happens is DL and DR, or at least one of the two, blows up. Okay. So the simple idea would be add a regularization here. So you will penalize that these matrices are getting too large, okay, or getting, one of the two should get too large if the algorithm does not converge. And there's a simple way to do that. You rewrite the matrix where you put M and M transpose in the two off-diagonal blocks, and here in the middle of on the diagonal, you put a matrix of all ones times a particular scaling factor, right? This is 1 times 1 transpose, so it's all ones, it's completely dense. And the fact that these two diagonal blocks are dense, you can then show that the conditions of Sinkhorn-Knopp, which is full indecomposability and the total support, are always satisfied. This is a graph problem. And it turns out that because of these two dense blocks here, this is always possible. I'm almost done. And so this is now a new modified problem. And you just apply Sinkhorn-Knopp to this modified problem. And you find then the diagonal scaling, which is symmetric, because this is a symmetric matrix. And from that, you recover these matrices. So it's again the same algorithm that you have to apply. And you have a regularized solution. And this always has a solution. Not only that, because of this link, we could also look at singular pencils. Singular pencils are pencils which are rectangular or square and have a determinant which is 0. And then the eigenvalue problem is a bit more delicate, but you can still do scaling. And it turns out that this regularized matrix, this will now be non-square. You can apply the diagonal scaling to that. Again, it's Sinkhorn-Knopp. A little modification because you have to take different norms for the rows and the columns because this is not square anymore. And we have to make not all norms equal, but equal to this vector here. And you can show that this does the thing. And this always has a solution again. Okay. This always has a unique solution if the regularization factor is different from 1, because then you have the full indecomposability and you have the total support. This is always satisfied. The eigenvalue sensitivity is a bit more delicate. We don't have the eigenvalue sensitivity because the pencil is singular. But there is a statistical study of these problems that is more, well, that makes it fall back on your feet. But I don't have time to go into these details. That's much more delicate. But as concluding remarks, we have new scaling algorithms, both for regular and singular pencils. The algorithms are Sinkhorn-Knopp-like. And the non-negative matrices to which you apply SK is actually very easy to construct. It's just sum of squares. It's Hadamard products. You always get a unique and bounded scaling. But the unregularized problem, if you don't do regularization, it usually works also fine, even though we cannot prove convergence, but we don't really need convergence. We just need a few steps of this algorithm. And this is something that we, for the moment, still don't understand, and for which there is an open problem. And I would welcome somebody like Philip to work on this, or any other student that Nick has. We want to solve the problem where you don't get to the optimum, you don't get full digits of accuracy for the scaling. You just want 1 digit. Okay, you want the correct power of 2 to be recognized in each column and row, and this should be enough. And since this, it's a hidden convex optimization problem, but over the integers, if you rewrite it after some transformations of variables. Okay, I'm sorry, I should address here also. This holds also for you guys. If you can solve the problem, then it's just as good as the data can solve the problem. Anyway, so happy birthday, Nick. And I want to terminate with a few references that are related to this analysis. Thank you very much.
Thank you, Paul.